have built-in functions and built-in.ars. This module defines all supported mathematical functions and constants. Example, it includes a square root, sine, cos, tan 2, power, factorial, logarithms, permutations, combination, and mathematical constants like pi and e. Let's run the project. Let's go to the terminal and let's run the cargo test. This project includes extensive unit and integration tests. This test suite includes ports of TinyExpr's original smoke tests along with the additional Rust specific tests. Here all the test has passed. Now let's go for TP. Static analysis is performed using Clippy. The project builds cleanly. Now let's format this project and let's check the formatting. Cargo F1 check, which verifies the formatting consistency. And then here's the cargo bench. The criterion benchmarks measures parsing and evaluation separately across multiple workloads. This includes simple arithmetic, nested expression, function calls, deep expression trees, and variable lookups. Let's go to the example.rs, which I have created a few examples. Here I have imported the hash map, which stores variables and their values during evaluation. I also imported the module from my library, imported the parser module from my library, which converts the mathematical expression into an abstract syntax tree. And then here is the expression which I want to evaluate. It calculates the square root of the sum of several squared values. Run it and for the result. This line prints in the output. When we run it without this output, and in the first line it shows the expression, and the second line it shows the evaluated result. Internally, the parser first tokenizes the input, constructs the AST, and then evaluated recursively computes the value. This demonstrates a complete pipeline of my project from parsing a mathematical expression to producing the final numerical result. This simple example shows the complete workflow of the library. Users only need to provide an expression, parse it into an AST, optionally supply variable values, and then evaluate it to obtain the result. So let's run my second example. The second example demonstrates one of the main advantages of the TinyExpr. Instead of parsing the expression every time, the expression is passed once into an abstract syntax tree and then evaluated multiple times using the different variable values. Instead of parsing an expression again, I simply update the variable values. Same AST is evaluated again using the new values, demonstrating how the parsed expression can be reused efficiently. For the first evaluation, x is equal to 3 and the expression and y is equal to 4. The expression calculates the 3 squared plus 4 squared, which is 9 plus 16, giving the result of 25. For the second evaluation, the x is 5 and y equals 12. The expression calculates 5 squared plus 12 squared. The 5 squared is 25 and 12 squared is 144. So the 25 plus 144, which is resulting in 169. This example demonstrates one of the key design features of the tiny expression. Parsing is performed only once, producing an AST that can be reused with the different variable values, which avoids the repeated parsing and improves efficiency when the same expression needs to be evaluated multiple times. The benchers. I also added a criterion benchmarks. The benchmarks measure parsing and evaluation performance independently. The workloads include simple arithmetic, nested expression, function calls, deep expression trees, and variable lookups. Separating parsing and evaluation helps identify performance bottlenecks more accurately. Here is my readme.md. The README documents the architecture, the grammar, supported functions, optimization strategy, testing instructions, strategy, the compatibility, benchmarks, engineering decisions behind the projects. It serves as a primary documentation for anyone using or contributing to the project. To summarize, the project successfully ports the original TinyExpr library from C to Rust while preserving its behavior. At the same time, it takes advantage of a Rust's ownership system, enums, pattern matching, and result-based error handling to provide a safer and more maintainable implementation. The project includes comprehensive testing, benchmarking with criterion, optimization through constant folding, and detailed documentation. So this is about my project, and thanks for watching.